Hello, everyone. Welcome to PyData Global 2021. I'm Conrad, one of the co-chairs of the conference. We're very happy today to have Vicente here with us, talking to us about introduction to quantum computing with Python and QS. Thanks.
Thank you very much, Conrad, and thank you everybody for your time. As Conrad said, my name is Vicente, and today I'm going to talk about quantum computing, Python, and how you can connect both of them using Qiskit. So within this talk, I will be talking what is quantum computing, what are the differences with classical computing, and I will go through some real-world applications right now. Then I will move to the IBM quantum environment, how to use it, how to get access. I will talk a little bit about Qiskit, and then we will go together through a notebook, seeing how to execute one very simple experiment using quantum computing. So first of all, a little bit about me. My name is Vicente. I've been 15 years working with data, mainly with anything that you can think of: relational databases, NoSQL, big data, on-premises, on the cloud. And in my free time, I like to play with other different technologies and areas. The main ones, genomics, cybersecurity, and this one that is quantum computing. So feel free after this talk to connect with me in LinkedIn or in any other platform if you are interested in talking about data and quantum computing. So first of all, let's go about what is quantum computing. For those of you that have heard about the term but are not that familiar with it, quantum computing is based on quantum mechanics. And quantum mechanics is basically a theory in physics that describes the physical properties of subatomic particles. So what that means? That means that when you go into the subatomic area, particles behave in a very interesting way. So basically, you have particles that when you are not observing them, they behave as waves. When you are observing them, they behave as particles, and they will collapse to a specific value. There are two main properties that we are interested in, and I will explain later. One of them is the entanglement. And basically, what happens when you are entangling two particles is that the value that one of them collapses, the other one will collapse to exactly the same value. So one example, I have two particles, one I have it on my own, the other one is in Australia, for example, in the other part of the world. So when the particle that I have collapses to one specific value, the one that is in Australia will collapse to exactly the same value. Another of the interesting properties of quantum computing is the superposition. Superposition is basically that one particle is going to have any value between 0 and 1. I will go deeper about this in other slides, but basically everybody knows the Schrödinger cat example. And this is what is based the superposition. So if we go to a very simple comparison between quantum computing and classical computing. Classic computing work with bits. And as you know, bits are 1 or 0, that's it. Because we are using superposition in quantum computing, a qubit, like what would be a quantum bit, may have any value between 0 and 1. And this is very important because we are going to use this later. And this is what gives its performance and its benefits to quantum computing. It allows you to store much more information using quantum computing than classical computing. Meanwhile, with one bit, you can store only one state, 0 or 1. With one qubit in quantum computing, you can store any value between 0 and 1. What you will have is a probability of that specific qubit being 0 or being 1. And again, I will go later deeper about this. There are other principles that we are very interested in quantum computing. You have phase, you have entanglement, as I said before, you have interference, but there is something that you must keep in mind, and here are the challenges that we have right now in quantum computing. Like all of this sounds awesome, it's more power, more storage, but there are some challenges. One of them is that quantum computing right now is in its infant state. What do I mean with this? Right now, if you want to code in quantum computing, you have to program circuits. So you will have to use gates. Imagine classical computing having to code circuits using AND or XOR gates. In quantum computing, you will have to do something like that. Additionally, right now, the computers don't have as many qubits as we would want to. If you read the news, there is now like a new company that is developing like personal computers for quantum computing. And I think that they have 5 qubits. So this is the stage in which we are now. Right now, there are only like 5 qubits if you want to get a personal quantum computer. And finally, there is the probabilistic nature. Because when you put your qubits in superposition, any value between 0 and 1, and what you have is a probability of that qubit being 0 or being 1, you can't run only once your experiment. You will need to run it several times and get the most common result. And again, I will go deeper about this later. So one of the challenges, as I was saying before, is that right now this is in its infant state. It's not like I can buy a quantum computer and I can get it into my house. What you have here on the left is the famous Google Sycamore quantum computer. And you can see it's taking like a huge room. And on the right, if we want to compare with the moment in which we had the classical computing at the same level, what you see on the right is the bomb, and is the machine that was used to decode the Enigma machine. So this is where we are right now with quantum computing. So, okay, it's very powerful. There are some challenges, but said that there are a lot of companies, governments, and areas in the industry in which they are pushing a lot of quantum computing. And this is because regardless of the challenges that we have right now, they see a lot of benefits now and in the short and long term. So I will go through some of the real world applications that you could use this. This is a very old news from the newspaper. I think that has already like 4 or 5 years. And this is when China was testing quantum entanglement for communications. So think on this. When we were talking before about entanglement, when you have 2 particles and you generate them together and you put them in an entangled state, and you send one to one part of the world and you send the other to the other part of the world, because you know that when one of them is going to collapse to one specific value, the other one is going to do it as well, is something that you should be able to use for communications. Imagine very fast communications and communication that nobody can interfere. So as you can see here is something that some governments are already testing. Additionally, there is a lot of performance with some specific algorithms. What that means, I'm sure that you have read some of the news, like people are trying to scale, like, oh, quantum computing is going to break our encryptions. Well, right now we don't have the power. There are not enough qubits for that to happen. But in the pace that we are progressing, there will be a moment in which quantum computers will have enough qubits to be able to break by brute force encryption. So as you can see, it's an area in which we want to keep our eyes on, that we are aware that there are some challenges, but there may be lots of benefits in performance in the future. So now that you know a little bit more about quantum computing, where is it right now? What are the challenges? Where is it going? I can imagine that you say like, okay, I am sold. I want to play with this. I want to start working with this. I want to get involved. So there is a very easy way to doing it, and that is using IBM quantum environment. So because it's not that easy to get a quantum computer, you will have to get used to it through cloud providers, similar to what you do with AWS, with Azure, with other cloud providers. You will need to use it through cloud vendors. So how do you do this? The easiest from my point of view, and obviously this is my point of view, is the IBM quantum environment. It's free, it's easy to use. You just need to create your IBM ID and you can start using it. It's going to provide to you 2 different ways of working with quantum computing. One of them is going to be through a UI. So you will be very visual working with circuits and creating them and executing. And the other is using Python and Qiskit with Jupyter notebooks. So this is how it would look, the visual circuit creation in IBM. As I said before, it's very visual. Something very interesting is that it generates automatically code for you based on the circuit. This code may be OpenQSM or Qiskit. The OpenQSM is basically assembly code. The Qiskit is the one that we are interested, that is available with Python. So let me try to share my web browser, and yes, let me see if it works. Happy days. And this is what you should be able to see when you log in the IBM Quantum environment. So basically, you would have the Quantum Composer, that is the one that I was talking for visually creating your circuits. So if I launch it, if you are a very visual person, what you see here is a circuit. You should be able to add gates, taking them out. Remember what I said before. The way in which this works for here is that basically you need to work with circuits. The way in which we code is with circuits. This is a very visual way of doing it. You can add different gates. And what you see here on your right is this environment creating the code for you. You can create it in assembly, or you can create it in Qiskit. So when you start working with this, when you start playing, it's going to be very interesting to play around, create your circuits, then see the different results that you would get from there. So this is the visual part. But if you are more of a coding person like me, let me come back to my presentation. What we are interested is basically in working with Qiskit. So there is that option as well using the IBM Quantum environment. You have what they call the IBM Quantum Lab, and that is basically Jupyter notebooks. That is something that I want all of you to be aware, and is that you don't need to use the IBM Quantum environment. I am doing this because it's easy for a presentation and it's going to make my life way easier. Everything is going to work perfectly. I'm not going to have any problem. But you should be able to use this on your local, just installing Qiskit. You can install it with pip, easy peasy. You install it, you can use it with your notebooks. But for this presentation, I will use the Quantum Lab. So once that you have started, you will be able to use Qiskit. What is Qiskit? Qiskit is a high-level code language created by IBM, and the idea is to be able to code quantum experiments using Python. It's open source, it's created by IBM, and it's the standard in all the IBM environments, and it's used even out of the IBM environments. So if you log in there, you should be able to use it as any Jupyter notebook. There are different notebooks there available for you. The one that is the more interesting is the getting started, is the one that I have been tuning a little bit, and is the one that we are going to go through together later. But before we go together through the notebook, there are some basics that I want you to be aware of. So the first of all, I will go through the different backends options that you have. Then I will go through how to create a basic circuit, how to execute it, and how to check the results. So first of all, there are different ways in which you can execute your quantum environments. You can execute it on the cloud using, for example, IBM Quantum environment. And what you will do is execute it in their quantum machines. That will be packed. They will be sent to a queue, and eventually it will be run in one of the quantum computers that IBM has. But the easy part is that you should be able to simulate it locally or in the IBM Quantum environment. And in order to do that, what we use is Qiskit Air. That is included in the Qiskit libraries. So once that you install Qiskit, it's available for you. And there are different simulators, different backends. The most common is the state vector. The state vector, basically what it's going to do when you execute your quantum experiment is return to you a vector with states for your quantum experiment. You can use as well unitary simulator. Basically what it's going to return for you is a matrix that is going to represent your experiment. And finally, you can use the assembly simulator. So there are different backends. We will execute an experiment through all of them, and I will show you the differences, but you need to be aware that there are these options for you. The one that is the most common is the state vector. It's the one that I usually use when I do my experiment. As well, you can run it in any quantum computer. So let's say that we start creating our base circuit. What I have here in this snapshot is basically the same circuit that I was showing to you in the Visual Composer. So what we are going to do is recreate that circuit using code, using Python and using Qiskit. Key for you, import Qiskit. This is the library that you're going to use. As you can see, it's very easy to create a quantum circuit with just 3 qubits. You just need to call quantum circuit. The parameter is 3. Boom, you have your circuit with 3 qubits. And then when you start doing is, because remember that we are programming circuits, what you will do is start adding gates to different qubits of your circuit. Here, what we do is adding a Hadamard gate to the qubit 0, and then adding a couple of C0 gates. So, easy to visualize your circuit. Qiskit works very well with matplotlib. So you should be able to basically using the draw function to show how it's going to look your circuit. And now this is the interesting part. You have different backends, and depending on the backends that you execute your circuit, you're going to have different results. What I am showing here to you is how you simulate in both backends, a state vector and QSM. On the left, what you see is how you should execute this circuit in the state vector. On the right is what you see how you would execute it in QSM. It's very similar at the end of the day. Basically, you are explaining to the code, okay, this is the backend that I want to use. On the left, we are using the state vector simulator. On the right, we are using the QSM simulator. You execute it and you get the results. And then, depending on the way in which you want to see the results, there are different ways. So on the left, if we have been using a state vector and you want to check the results, what you're going to get, as I said before, is a vector with the different probabilities for each one of the states. So as you can see here, we were putting it in superposition, in entanglement, sorry. So you would have half of the probability for 0, 0, half of the probability for 1, 1. If you want to visualize this, this is how you can do it. Again, using matplotlib. On the right, it's even easier. You don't want to get any visualization about the states, you just want to see the results. So what you do is execute the experiment 1,000 times, and then you get the counts for the different results. Remember, because what I said before about being a probabilistic nature, because once that you put your qubits between 0 and 1 in that state, what you're going to get is a probability. This qubit can collapse to 0 with a probability of 50%, can collapse to 1 with a probability of 50%. So when you execute this experiment a number of times, you will have what you see on your right. 50% of the times, more or less, 0, 0, 50% of the time, more or less, 1, 1. Again, this is because the probabilistic nature of the quantum computing. And now, before going to the next steps, I have time. So what we are going to do is we are going to run it on our own. So if we go again here, we go to the lab, as I was explaining before. Let me launch my server. Time it out. It's going to make me look bad. This is what happened with the typical demos. Okay, let me launch my lab. And basically what I am launching here is Jupyter notebooks. So you're gonna have different options in the IBMQExperience. Basically, you're gonna have the option of running Jupyter notebooks, different versions, but the one that we are interested in is getting started with Qiskit. This is the one that I have been showcasing with a snapshot, but we are gonna run on our own. So once that you open this, and this is available for all of you, the easy part is basically to import Qiskit. We do it, no problem at all. This is how you create your circuit with 3 qubits. It's basically creating your circuit, and this is where we are gonna recreate the visual circuit that I was showing you before. We are adding a Hadamard gate, we are adding different CNOT gates, and we want to visualize it. So if we go to visualize it, again, this is how my circuit is gonna look. Now, this is the interesting part. Let's see how we execute it with different backends that I have been showing before, and let's see what are the results for each one. So First of them, we can use the state vector simulator. This one, remember what I said before, is going to return to you a vector with the probabilities for each different state of your circuit. So we request this backend, we run our circuit, we get the result, and then we want to see how it looks. Because we have our circuit in an entangled position, both qubits are going to collapse always to the same value. So what this means is that our result is going to be always 0, 0, 0 or 1, 1, 1. And this is because our qubits are collapsing always to all zeros or always to all ones. Because the probabilistic nature, what you have is a state in which 50% could collapse to 0, 0, 0, 50% could collapse to 1, 1, 1. So this is what you can see in this visual representation here. If you execute it in the unitary backend, what you will have is a matrix representing the state of your circuit. But the most easy to follow the results is the OpenQSM. And I am going to show you why. We execute it in our OpenQSM backend. We execute it 1,000 times because we are interested in see the distribution of our results, and we get the counts. What you get with the counts is the number of times that the results happened and the number of times that the result happened. Because we know that we are in an entangled position, when we execute this and we get the results, we are going to get roughly 50% of the times 0, 0, 0, 50% of the times 1, 1, 1. Again, because the probabilistic nature, if I execute this again, the numbers are going to change slightly. And this is because you're not going to get always exactly the same results. As you can see, they change it a little bit. If I execute it again, let me go with it. The counts will change again, but always they are going to be roughly 50 and 50%. And this is because me personally encoded in this circuit an entanglement in which I know that all the qubits in that circuit are going to collapse always to 0, 0, 0 or to 1, 1, 1. So, okay, let me come back to the slides. And now that you know what is quantum computing, why it's so interesting, you are a little bit more familiar with Qiskit. You should be able to install it locally or to use the IBMQExperience. And you are able to go there and check different notebooks that they have for starters, or you can even work with that, with your own ideas. So what would be the next steps? Let's say like you love this and you say, Vicente, I am all in, I love it, I want to play with this. So my recommendation for next steps is set up your environment. You don't really need to use the IBMQExperience environment. You should be able to install Qiskit on your local machine and be able to execute it. Read some material. I really recommend this book. I'm not getting any fee for that, but I do really recommend it. It's really good. Programming Quantum Computer brings a lot of examples, a lot of different algorithms that you can play with. I do recommend it. Take a look and play with some of the algorithms and some of the code samples that they provide. And yes, my final advice is to experiment. Play around with it. Right now, I am a data person, so I am playing with different data processing experiments. They are a little bit complex. This is why I not show it here. It would take like a little bit of time to explain the different algorithms and the different things that I am trying, but you can do the same. You can go in your own laptop, you can play around, you can install it, check it out, this book, get inspired by it, by some of the tutorials that you have in the IBMQExperience. Best of all, if you have any doubt, you have any problem, any doubt about data, about quantum computing, feel free to connect with me in LinkedIn, and I am happy to talk about this. This is one of my passions, and I am happy to answer any question in the Slack channel or connect with me offline through LinkedIn. Yeah, come back to me with any question, any doubt you may have. I want to thank you for all your time, and this is the end of my presentation. Within time, I let 5 minutes. So thank you very much, everybody, for your time.
Thank you, Vicente. I'll stop the recording now.
Okay.